hold a little bit to the schedule. We will, there will be a total of 10 talks this afternoon. We will more or less hold to the time, but if there's a lot of questions, we'll try to have them fielded since we really have nothing to go to at 2:35 or something like that in the afternoon. We'll let it go maybe a little longer. The first talk this afternoon is a contribution from University of Illinois at Chicago and also Argonne National Laboratory. J.R. Regalbuto and C. Allen, and Professor Regalbuto will give the presentation.
Maybe we can judge the quality of the program by the Friday afternoon attendance quotient. The quotient, which is the number of attendees divided by the number of talks. And since we're well greater than 1, I think we're doing okay. I'll start off by noting, can the focus be adjusted a little bit? That one of my students who contributed a great deal of the work was inadvertently left out of the program, and that is Voy Dada. Another one of my students who has done some of the work here is Jim Gold Kim. The in situ electron microscopy that I'll be presenting has been performed in collaboration with Charlie Allen at Argonne on the HVEM there. And I'd like to acknowledge the funding of the Amoco Corporation as well as the Illinois Department of Commerce and Commercialization. Well, it goes without saying that molybdenum trioxide is a very valuable catalyst component used as either a catalyst itself or as a promoter of a second component as well as a precursor for a sulfide form, for instance, in a hydrodesulfurization catalyst. And it's of great interest if we can actually control the morphology of molybdenum trioxide for the purposes of one of these three roles. The current sort of status, the present status in regards to the dispersion of molybdenum trioxide on silica is that in fact you can't redisperse molybdenum trioxide on silica. There have been experiments done where bulk molybdenum trioxide has been mixed with bulk mixtures of various supports such as silica, titania, zirconia, and alumina. Then you calcine at a high temperature and look for any sort of redispersion. And people have found that just, while molybdenum trioxide redisperses over all the other supports, it does not over silica. Well, to present the results of our work up front, we have found that if you calcine at a lower temperature than what people normally do, that is, the normal calcination temperature is somewhere around 500 C, 450 to 550 C, for example, which results in the orthorhombic phase of molybdenum trioxide. If you calcine at 300 degrees C, you get a metastable hexagonal phase. And with this phase, you can do a whale of a lot. Its behavior is dramatically different from the orthorhombic phase. And I will show that today with, first of all, some X-ray diffraction data. Secondly, I'll go to the in situ electron microscopy and then go to some conventional transmission electron microscopy with Valladate's model spherical non-porous silica spheres. Finally, I'll mention some of the catalytic ramifications that I think can be derived. First of all, I mentioned that I'm talking about here relatively high-loaded catalysts. We wanted to be able to look at these things with X-ray diffraction as well as electron microscopy, and so we wanted to put a lot of material there. The breakthrough concentration between a monolayer type catalyst and a bulk molybdenum trioxide type catalyst is typically thought to be about 1 atom per square nanometer. We have formulated the real catalyst and the model spherical catalyst such that we have about 4 atoms per square nanometer, or that the ratio of bulk to monolayer should be about 3 to 1. So there should be plenty of material there to see. In all cases, therefore, we start out with a poorly dispersed and amorphous precursor, and that's the starting point for lots of things. Okay, I've got 2 X-ray diffraction slides here that I'll spend a little bit of time on because they really tell a very complete picture. First of all, if we take the unsupported bulk precursor, which is ammonium tungstate, metatungstate, and just calcine that bulk powder at 500 degrees C for 2 hours, we get the orthorhombic phase, which is what everybody sees. If we impregnate the silica support with the same precursor, calcine at 5 hours, we get the same crystalline phase. And this is where the observation of the hexagonal phase might be a little tricky, because if you calcine the precursor, the unsupported precursor at 300 degrees C, you also get mainly the orthorhombic phase. And you see little bits of the hexagonal phase appearing here. But it's not until you use the silica support and calcine this at 300 degrees C that you largely end up with the hexagonal phase. Now, the differences in behavior of this hexagonal phase and the orthorhombic phase here are quite striking. And that is seen from this next set of X-ray diffraction data. I've repeated, first of all, the supported hexagonal phase, which I'm calling bulk hexagonal, meaning we have large hexagonal crystallites here. And up here we have the supported but very large or bulk orthorhombic crystallites, which have been formed by the 500 degree C calcination. Now, it is possible to convert the bulk hexagonal crystallites formed at 300 degrees C at 2 hours into the bulk orthorhombic phase by calcining the hexagonal crystallites at 500 degrees C. The conversion is irreversible, however. If I take the 500 degree C sample, the hexagonal sample, and calcine it at 300 degrees C, there's essentially no change. Now here's where the dramatic difference comes in. If I calcine the hexagonal catalyst for a continued length of time at 300 degrees C, now going from 2 hours for an additional 4 hours, the crystallinity almost disappears. We have what I'm calling now a dispersed. It's not properly a hexagonal phase because it's mostly amorphous. Okay, so we have a very dispersed catalyst. Then what we can do here is calcine this sample at 500 degrees C, and we'll get the dispersed orthorhombic crystallites, or any crystallites present will be converted to the orthorhombic form. And then what I've shown finally at the top is that, well, first of all, if you continue to treat this, calcine this dispersed orthorhombic sample at temperatures below about 300 or 400 degrees C, it's perfectly stable. However, if you calcine this at 500 degrees C, they do eventually center up into the orthorhombic phase. So this shows that the thermodynamically favored state of the, starting from the hexagonal phase is a dispersed form, whereas the molybdenum trioxide prefers thermodynamically at 500 degrees C to be in the form of bulk crystallites. So what we've got here is a low temperature pathway to produce, to control the dispersion of molybdenum trioxide. And this is through the initial formation of these metastable hexagonal crystallites. Okay, from this point we have augmented and supplemented the X-ray diffraction data with microscopy. And I'll first show some in situ electron microscopy of now planar catalysts. We have the planar silica support, and I have, I call it MoO3 precursor. This is the ammonium metatungstate, which has been dried. I'll have you note also that this is very low magnification. There's a bar, I believe, for 1 micron. So we have really huge particles here. There's always a trade-off if you're talking about in situ microscopy. The resolution suffers greatly as the beam travels through this thick gas layer. Now, this particular particle here was used for focusing and alignment of the instrument, and so it got coated. It was relatively highly exposed to the electron beam, and it got coated essentially with a layer of goo and did nothing for the rest of the experiment. And this was typical of lots and lots of runs. It was only after we started heating, and then when we had reduced the beam exposure to very low levels, that we went to another area and saw that the spreading had begun. And so the precursor initially, well, it starts forming these thin discs here through 30 minutes, 60 minutes, 70 minutes, etc. And the difference between here and here is that this large initial clump itself converted into a thin disc. We can monitor these with electron diffraction, and we see that these are thin discs of the hexagonal phase preferentially oriented with the basal planes the basal planes parallel to the silica substrate. And so here is again a demonstration of the spreading of the hexagonal phase of molybdenum trioxide on silica with a low temperature calcination. If we try to look at the conversion from the hexagonal to the orthorhombic phase, we first jacked up the temperature to about 500, and after only 10 minutes we had a very rapid spreading of the material, but that still wasn't enough to tip the scales, and so what we did is we added a further increase, a local increase in temperature by focusing the beam on this crystallite. And then in a matter of seconds, before you could snap your fingers, we had this transformation to these orthorhombic needles. And we reanalyzed this with electron diffraction and got the pattern for the orthorhombic form. Now we've also used the non-porous spheres, silica spheres for this, and I'm a big fan of this. As Abaya Date has mentioned, these are great samples to characterize in the microscope, and they have sufficient surface area that you can put the same samples in the reactor, which is what we're planning to do for a number of studies. And what we're showing here is an illustration of how to prepare a well-dispersed sample, an ultimately well-dispersed sample. We start out with a huge crystallite of the hexagonal phase, take it through an additional calcination at 300 degrees C, so most of it spreads, and then finally we lock it into place, if you will, by calcining at 500 degrees C. So we start from this to this. On the other hand, if we start again from the bulk hexagonal form and immediately calcine at 500 without this continued calcination at 300, not only do the crystallites not spread, but in fact they seem to grow a little bit to aggregate with some of the material that was stuck over here on the grid bar. This is a grid bar, and this is some material that's in between the grid bar and the sphere. What I've shown in these last few slides is what I think is a nice technique of viewing the same region of sample as a function of pretreatment. You can put these samples on a finder grid, and it's relatively easy to go back after each treatment and look at the very same crystallites. And I think that gives you a very good handle on what's going on. Finally, if you start from the orthorhombic phase, which is formed after a 500 degrees C calcination, and calcine this for another 6 hours, you see essentially no change. So we can use this to rule out any type of volatilization mechanism, I think, because if there's no volatilization at 500 degrees C, there's certainly not going to be any at 300 degrees C. So the catalytic ramifications, I think, are this. We've discovered this low temperature pathway to control the morphology of molybdenum trioxide on silica. Even highly loaded catalysts with the poor dispersion can be made highly dispersed. And I'll also mention that we have come up with a new morphology of molybdenum trioxide. We have gotten an amorphous form that is multi-layered. Previous to this, I think you could only have a monolayer type of molybdenum trioxide or a bulk. A monolayer amorphous type and then a bulk. Since the loading that we've used in these catalysts is greater than 1 atom per square nanometer, we've got a couple of amorphous monolayers in the material here. And I think this might have interesting catalytic activity, which could be appreciably different from either of the other couple of types. Excuse me. Now also, in regards to, say, hydrodesulfurization or other promoter types of reactions, if you start from the poorly dispersed hexagonal phase, the spreading of molybdenum trioxide over a second immobile component might be controlled. Now I've used an example here, cobalt moly catalysts, and we've already looked at cobalt on silica, and by golly, that stuff just stays in place. The same can be said for platinum here. So the idea is you can control the extent of the oxide coverage of moly on the second immobile component, and hope that it stays more or less in place during the sulfidization step to actually control the amount of interaction between the cobalt and the moly phases. Now, I don't have this information for these catalysts, but I will show you something that's from platinum molybdenum trioxide, before and after the calcination. I hope you can see here that we have about a 40 angstrom overlayer. I would never hope to be able to see this with we're using a JUL 100CX microscope here with an analytical pole piece at that. So it just so happens that molybdenum trioxide forms very thick overlayers, or we never hope to see them here, as the careful high resolution work that we've seen before has shown. But at any rate, you can create overlayers on platinum with molybdenum trioxide. And as you do that, now you can look at the spillover rate. You can run hydrogen over your sample and watch the rate at which the hydrogen bronze is formed. So the non-calcined sample, the hydrogen uptake rate looks like this. As you calcine at higher and higher temperatures, and at the same time perform a CO chemisorption experiment at the end of the experiment to figure out how much free platinum surface area is, you see that the chemisorption uptake decreases as these overlayers form, but that the hydrogen uptake rate through 100 degrees C calcination, 200, 300, 400, 500, etc., increases dramatically. So this is more evidence that you form these overlayers, and I'd say that here the hydrogen, the overlayers are acting as something like a solid hydrogen spillover bridge to assist in this rate determining step here. And so you can think of also kinds of useful applications in hydrogenation and dehydrogenation experiments here. So the conclusions are that a hexagonal metastable phase of molybdenum trioxide forms on silica, and only on silica, principally on silica at least, with a 300 degree C calcination of the precursor, and this phase can be easily and controllably dispersed by additional low temperature calcinations. And I haven't gotten into it, but the observations point to a surface diffusional mechanism. The hexagonal phase is irreversibly converted to the orthorhombic phase at 500 degrees C, which is more or less stable at moderate temperatures, say below 300 or 400 degrees C. You'd have something like a kinetic limitation here to maintain the stability of this dispersed phase. And so the dispersion of molybdenum trioxide can be controlled or adjusted and then locked into place, if you will. And I think that all types of reactions could be addressed by this type of control of morphology. Thank you.
Question?
Do you plan to study the effects of co-impregnating molybdenum and cobalt on these supports?
Yes. Yes, we certainly do. That's the next work. And we want to use a high-resolution microscope for that, too. To look at, because we want to look at the changes going from the calcined state to the sulfided state of these overlayers, which are going to be on top of the cobalt and crystallites. So we're going to need the best resolution we can get there. And then we're going to put the same samples in a microreactor and get the activity there. So that's the way we hope to relate the structure to the function.
In the planar views, those particles look spherical. Whereas in the views on the curved particles, I didn't see any of those kinds of moly oxide particles. Can you comment on that?
The magnification was tremendously lower in the case of the planar substrates. We're looking at huge, even tenths of microns or even up to micron, big patches of the molybdenum trioxide in the hexagonal phase. And one of these little needles that we saw in one of the spheres would be just a tiny dot there. So the scale of things is a lot different. I think that has something to do with it. It's very hard to detect the diffusing species with the 100CX. Sometimes we can see, sometimes the layers are as thick, say, as 40 angstroms or so, but it's pretty difficult.
Could you comment on what you think would happen after you made a conversion to a sulfide form? That's one question. Another question is, under operating conditions, say either oxidation, catalysis, or reforming, you'd be at temperatures which would exceed your stabilization. You'd start centering again. Can you comment on how you think that this initial dispersion, you could lock that in to keep from happening ultimately?
Well, first of all, I wouldn't know what's going to happen to the sulfides, how stable they would be. So that's sort of an open question. Hydrodesulfurization, well, I noted that a couple of them were done at about 350 C, which is a temperature at which I think this would be stable. At least the oxides are.
What about oxidations?
Oxidations, that remains to be seen. one thing we've done is we have looked at the effect of calcium for this series of platinum molybdenum trioxide experiments that I told you about. The ones I showed here were just a 1 hour calcination, say at 400 degrees C, and that shows that you cover about a half of the platinum with a 1 hour calcination. We also did a 2 and a 6 hour calcination at 400 degrees C, and we got the same results. So it seems to be that there's some kind of equilibrium reach. With a 500 degrees C calcination of the platinum, you cover about 90% of the metal. And it's interesting to see that the uptake rate is still high, even though you're covering up the majority of platinum. But at any rate, with additional time at 500, you still have about the same amount of platinum left. So maybe there's some kind of equilibrium coverage. That might be far-fetched, though.
One last question, Howard.
Do you have any idea of what you propose as the migrating molybdenum oxide species, and why is it present? Why is it available from the hexagonal phase and not from the orthogonal phase?
That's a very good question. And this class of of material is interesting because unlike titania, the spreading occurs during the calcination. You don't have to have a partially reduced species. Now, monomeric species are known to exist over silica and alumina supports, and I would say that it's some type of species. I would also conjecture that the temperature of the silica surface has something to do with it. The particles might form over both, but at 300 degrees C, the stuff might want to spread over the silica, but at 500, it seems to want to center up. So it might not be so much related to the type of crystallite it comes from, but to the temperature of the silica surface. Because these overlayers on platinum can form whether we use the hexagonal or the orthorhombic phase. Which is to say that it comes to a question of thermodynamics. The surface free energy of molybdenum trioxide is lower than silica. I would say, but in the same term, it's also lower than platinum. So, I guess what I'm saying in summary is that I think it's a question of it's a surface diffusion phenomenon, and it has to do with the equilibrium concentration of the molybdenum trioxide over the silica, principally, as opposed to the phase that it came from.
Okay, thanks again. Our next paper is entitled Comparative Behavior of CO Adsorption on Rhodium on Alumina and Rhodium on